Okay, so we are finishing up on chapter 2 today, but uh, we've been discussing more specifically these four perspectives outlined by Daniel Rosiak in Sheaf Theory Through Examples in section 2.4.2, four ways of acting as a pre-sheaf. And we've discussed to some degree each of perspectives 1, 2, 3, 4. So this viewing pre-sheaves from a process-based perspective, such as iterating between elements of the same set or different sets, extracting boundaries, like going from edges to vertices, for example, a pattern that applies in quite a few contexts. Conditions, how probes of a space relate to each other. This related to this idea of doing Hom finding of a pattern in some C set, in some pre-sheaf. Maybe it's a representable. And then because there are maps between these representables or maps between different patterns, you can relate one to the other. And that's going to be a fairly important perspective since sheaves. But it's really this last one, the one for today. Viewing pre-sheaf actions as restrictions, that is going to be a central theme within the context of sheaves. And for those of you understandably perplexed by the shift back and forth pedagogically between C sets, on the one hand, where we have a functor mapping from some schema category C into set or fin set or what have you, some category of sets, on the one hand, versus pre-sheaves where we go from C up into some set-based category. I've been kind of going back and forth between them, recognizing that often it's easier to think in one, in other cases it's easier to think of the other. But you'll really find here the pre-sheaf perspective very, very helpful. Arguably more so than we've seen in previous cases. So I want to talk about this. And this particular section was not terribly long. It was example 55 on page 80 through the end of, really for 2.4, the top of 85. But then there's section 2.5, which is a more philosophical reflection on these four perspectives, which is quite nice. But I wanted to talk about these examples. So Daniel Rosiak gives a set of examples. And some of them have a deep mathematical history, like this idea of looking at continuous functions over intervals and relating them, continuous functions over a broader interval with continuous functions over a shorter subinterval of that. But others of them get more to our applied work. Like there's this case of kind of products in stock during different periods of time, or laws that hold across jurisdictions and relating those for broader jurisdictions and sub-jurisdictions. So I did prepare some slides on this area, and I wanted to go over them. And like the other slides, I've been putting actually quite a bit of effort into curating the slides on the site, and I've done a couple updates for some of them. And I'll be putting these ones on there, hopefully today. The first example is example 55 in the book, where Daniel Rosiak is relating continuous functions, indeed, over a broader period, to continuous functions over a shorter period. And he introduces some of the core ideas underlying sheaves. And I want to talk about them and start introducing so we start to become conversant. So he also arranges suggestively in this and subsequent examples in the book a certain diagrammatic notation we're going to find very handy. And it's this one shown here, where we have something at the bottom and something at the top. Probably the most important examples of it would be something like this, or something like this, or something like this. And we're going to come back to them. But fundamentally, we're going to be relating here over different periods of time the set of continuous functions. So these would be functions that match some notion of continuity. Maybe they have no direct discontinuities in them, for example. And we're considering them over the interval 0 to 6 versus the interval 2 to 4. And maybe this is time, for example. So you could think of these as kind of waveforms varying continuously over the interval 2 to 4, and these as waveforms over the interval 0 to 6, say time. Now, one thing I want to draw your attention to centrally in the examples I'll be talking about today, recurrently, I'll be coming back to this point, is that I think we'd all agree that interval 2-4 constitutes a subpiece of interval 0 to 6, right? It's a subset of that interval. We'll use the term, there's an inclusion relation from a smaller subpiece to a larger piece, of which it is a subpiece. And what I want to draw your attention to here is that within this example, there's this relating of the continuous functions over a broader set, a broader time period, to those over a smaller time period. And one of the things that Daniel Rosiak emphasizes, the author emphasizes for this, is the fact that there's a notion in which, in this case, in the subinterval 2 to 4, there's less time in which things could go wrong with the function. So to put it another way, that put it way too crudely, but if there's a function that's discontinuous over this broader interval, it might still be continuous over this interval, right? So maybe there's a discontinuity at time 1 in some function. It might not be in this set, right? Correct? Right? It wouldn't qualify to be in the set of continuous functions over 0 to 6, but it would be in this, the subset of it from 2 to 4 could still be in here. Do you agree? So it's certainly not the case that this is a subset of this. There's going to be some things here which are not. There's some functions which would qualify to be continuous over 2 to 4, whose broader extent it is not continuous over 0 to 6. On the other hand, for every function up here, it may be that two functions differ up here in the broader interval from 2 to 6. Like maybe they differ, so they're different functions over this interval, but maybe they only start differing in the interval 5 through 6. They diverge there. And before that, they're the same. Those might map down to the same function over the interval 2 to 4, like they coincide, right? So we have this relationship between these functions via what's called restriction here, okay? And I want to highlight here that this restriction map is contravariant in this one. This goes 2 to 4 to 0 to 6 because it's inclusion. This is included in that. This restriction map goes from this broader interval to the narrower interval. And so it's restricting, in this case, quite literally, these functions down to be functions over this interval. And you'll notice the notion here, or the notation here, is a familiar one if you remember back to math courses, where they'll talk about a function restricted down with this sort of bar notation, bar sub, like if you have a function f, and you consider a restriction from that from u to r to be something to v to r, function f goes from u to r to reals, and the restriction to v goes from v to reals. So in other words, its domain is restricted from u to v. And so we're restricting the domain of these functions from this to this. But there might be some here, for example, that are not in this set, right? That are not in this set in the first place up here, and that do qualify here. So I want to note here one thing that he's done is he's shown these intervals directly with the data on them. We're going to start making a distinction there between the sort of pieces of the different spaces in which they're located, here 2 to 4, here 0 to 6, and the actual data about those spaces, which are called stalks. They're going to be called stalks, okay? S-T-A-L-K, yes. Okay, so these are stalks here, for example, that we're going to be coming to. And when I draw them here, these are stalks. So they're a stalk from this, and they represent the data for this space, for this place, as it were. So here we have a place 0, 2 to 4, and this represents the data. But in many cases, we'll actually diagrammatically show it like this. And the stalks notation is very, very common, visually too. Okay, so let's consider this second example, or it's actually not a second, it's a third example, I think. And he's considering different intervals of time. And you'll notice that these are not necessarily just joint, January 1st to March 1st, February 1st to April 1st. Clearly, some of this interval lies in overlap with this one. Similarly, this interval is overlapped with this one, etc. Okay. Now, what he's showing from this kind of cover of this period of time in which we're interested here, you'll notice that he's constructing some subintervals. So if you take the intersection of this one and this one, for example, you get an interval between February 1st and March 1st, right? This one goes from February 1st to April 1st. This one goes from January to March. And so there's a intersection. That's this interval, right? And same thing with this interval here. Same thing with this interval, etc. And this shows an interval from January 1st to February 1st that's not represented here. Okay. So these hold intersections, and you'll notice that there's some intersections between them too. For example, March 1st is in both of these, so it's up there. Now, this space has some structure on it. This space has structure, and I want to highlight that these relations are, again, inclusion relations, right? So February 1st to March 1st is included within this interval. Are we okay with that? This is included in this interval. February 1st, he is not shown at, if we want to be careful notationally, we probably do February 1st, comma, February 1st in interval notation. This is an interval consisting only of February 1st. He just, to simplify writing it, he put it like this. But that's included in these. Are we okay with that? This is going to be extraordinarily common. In fact, it's going to be ubiquitous for sheaves. We're going to see this again and again. This is going to be a pattern. Now, there, we're going to have a formal topological space, which we don't have here. We actually don't have a formal topological space. We're not considering intersections and unions. There's not the entire space as an interval, and there's not the empty set as an interval. But this general picture where we have different spaces and we have inclusion relations between them, and we have intersections between them, this is going to be a dominant feature of our experience with sheaves. So this is the underlying space on which, and this is key, we're going to assign data. This is just where the places that data can live, or to which it is relevant. So in this case, it's time intervals. In other cases, it could be spaces, like places. These could be regions of the province. These could be different provinces or subsets of provinces of Canada, as we'll see. These could be different sets of cities within Canada. They're going to be places to which the data is relevant. Are we okay with this idea? And there's going to be inclusions between them, and there's going to be some formal structure on it. Here we have this intersection property that governs these, and we have inclusions. I hope you realize this. We could formalize this with a categorical structure. The inclusions would be morphisms. We could compose morphisms. February 1st to February 1st is itself an inclusion into this one, right? Okay. So, and simply March 1st is an inclusion in this one. You could go like this. Moreover, you might start to think about this. There's some commuting properties. Well, if this is a pre-order, it automatically has to commute. So if I went like this, March 1st to March 1st, down to March 1st, April 1st, took where it was included here and then included that in here, it would need to be the same of necessity going this way and this way. Are we okay with that? So going either way is the same. And what that's going to mean is once we consider functors to a data space, which we're about to do, commuting has to hold in that data space. It has to be the case that if we transform the data for this to the data for that and the data to this, that it has to be the same as transforming the data to this and then to this, which is a central property of sheaves. Just hinted at that one of the most defining property of sheaves. Okay, so I'm having trouble figuring out. Can you still see my screen? Okay, Okay, so this is what we've been talking about, the structured space with inclusion maps between. As always in category theory, our focus is on the morphisms, especially not just the places, but the relationships between those places in the form of these morphisms. And what you're going to see in this presheaf is these places now, or these spaces, or these, in this case, intervals of time, they have data over them. And this data in the book is described as representing the set of products that were in stock throughout a given interval. Mind you, mark my words, throughout an interval, right? So for the interval February 1st to February 1st, maybe these sets of products were continuously in stock for this. Jeff can probably relate to this from his staple.
Sometimes something's only in stock for an instant.
That's right. And you'll notice that here's another interval where there's a set of products in stock, but you'll notice that the morphisms here, so each of these is a stalk of data associated with a given place here, a given space, a given place you could be. In this case, they're intervals of time. So do you see this? So there's some data associated with each of them. But what's especially should be attracting your attention is these arrows. Here too, you have arrows that reflect these arrows. But there is a difference if you consider. What's the difference? We could say ABC is over this one, ABCF is over this one, ABC through A through G is over this one. But what's the difference? The arrows mirror these, but in a certain way. What's the way? They're contravariant, right? So down here, we have an arrow going from February 1st to February 1st to March 1st. That reflects inclusion, right? This is a sub-interval of this. Do you agree with that? But up here, the arrow goes the other way. It goes from this to that. And it's what's called, again, a restriction map. Now, is this restricting the data down? No, it's restricting the space over which we're considering the data. This is a sub-interval. Is the data becoming smaller here? Like, are we like just projecting down? No. This is not a projection. This actually has, for example, G in it that's not here. This has E in it that's not here. So we're not restricting in the sense of throwing away data. No. We're not just projecting away data in all cases. No. Why is it that, intuitively, why is it that this, for February 1st, if we consider products continuously in stock, consistently in stock throughout an interval, why is it that this is larger for the interval February 1st compared to February 1st, March 1st?
Less purchase activity.
Less purchase activity, yeah. An item could go out of stock on February 2nd, for example. It wouldn't be on this list because it went out of stock at some point in this interval, but it would still be on this list because it was in stock for February 1st. It just, if it went out of stock on February 2nd, it wouldn't qualify for this list, but it would for this one. So in some sense, there's more restriction on this because it's a broader interval. There's more constraints would be the best way to put it. I don't want to get the terminology mixed up. There's more constraints on this because you've got to be in stock for February 1st, for March 1st, for February 2nd, February 3rd, February 4th. Got to be in stock all throughout this interval. And that's more picky. That's more of a tighter stipulation than just being in stock for February 1st to February 1st. Are we okay with this? So this restriction map is not a projection. What is it doing? Well, it's mapping A into A, B into B, C into C, and F into F. After all, something could be continuously in stock for all February 1st to March 1st, only if it was continuously in stock for February 1st to February 1st as well, right? We just said that. Like, for it to be in stock from February 1st to March 1st, it has to be of necessity in stock for February 1st itself. And so it's guaranteed to be here. And this is an inclusion of this in this one. But you'll notice the order is reversed. It's a restriction at it's contravariant, right? Are you comfortable with this? Same thing was true here. Same thing is true here. And you'll notice, again, as a pre-order, this property. So the fact that it's a pre-order means this commutes. These are functions, actually, in this case. Excuse me. These are functions now. This is not a pre-order up here. I misspoke. I said this is a pre-order. This is a pre-order. You'd agree this is a pre-order through inclusion? Is this a pre-order? No, these are sets. These are actually sets. And if you have sets, and I'm saying A goes to A, B goes to B, C goes to C, F goes to F, what does that sound like? That's a function. So these are sets and functions. But this is a functor that maps up to the stalks. So that means that this square, so to speak, commutes. This parallelogram commutes. This diagram commutes. So if I consider A's relation to the A in this broader interval here, and then map it up to as it was on. So this is the broadest interval of all. And if I go and now restrict it down to February 1st to March 1st, this A is the same as that A. And then I restrict it down to February 1st, it's the same A here. But if I had this A for January 1st to March 1st continuously in stock, and I consider it related to this one from January 1st to February 1st, would be this A, and then map to this A. And they have to coincide. They have to commute. So this is an inclusion relation from smaller to larger. Here we have an inclusion of the set of products continuously in stock from a larger time frame is a subset of those continuously in stock for the smaller set. And there's a, if we consider as a function, there's a injective map here. There's a monomorphism. This is a subset of this. Now, you could consider this instead of products continuously in stock. You could imagine this being customers who maintained corporate purchasing accounts at Staples all through this interval, right? And over a shorter period, if we're considering to be on this list, they have to have it over the entire period, over a shorter period. There's going to be a set of customers who are continuously there that are going to be a superset of an interval that includes that, because they have to be there each and every day. So for a single day, there's got to be everyone who's in it for the larger interval has to be in it for each and every day. All right. This could be the sales in effect all throughout those periods. Instead of products, it could be sales in effect. So there are some sales that are only on for a particular subset of days, say February 1st to February 1st. But then there are some that are on for shorter intervals and some that are on for longer intervals. And in general, if a sale was on this entire time period, it is going to be on for any subset of that time period, but there may be some on for the subset of the time period that weren't on throughout the entire time period. Are we feeling comfortable with this? Yeah. Okay, let's talk about another sheaf here. Or sorry, another thing of this form, another presheaf. Sort of precision, like we're going to be going with the sheaves. Okay. So here we have a preorder in the base of regions. Maybe considered for a given month. And maybe, so we have the empty set, we have British Columbia, we have Alberta, Saskatchewan, and then we have various subsets of provinces. There's a pre-order. What does a morphism mean here? Well, it means inclusion, right? This is a subset of that. You've seen this before. Automatically commutes, right? It's a thin category. Is either 0 or 1 morphisms from any one object to another. Composition just comes from composing the inclusion relationship. We just don't draw it, but of course there's one from BC to this one, right? We comfortable with this? Category, nice category, nicely behaved category. Okay. Now let's consider our stalks. For those not familiar with it, this term stalk comes from sheaves of wheat. So we might have a bundle of wheat, and these are the stalks of the wheat. So this is a little bit of ground over which the wheat grows. And suppose we have the intervals for the month we're considering of the number of people the cumulative number of COVID-19 cases for that month for the appropriate jurisdictions here. So for BC, we have some value for the number of, say, lab confirmed COVID-19 cases in BC, for Alberta, for Saskatchewan, for Alberta and Saskatchewan. This is a tuple, so a pair of values here. And this is a 3 tuple, 3 values. Are we okay with that? So this is values over this, a particularly simple set-based value. Are we okay with this? So we have 3 values. We have 1 for each of the elements of the set. And what I'm telling you, though, is that some of the most interesting things here as normal are not these values, but the relationships between them. What is the relationship? Well, in this case, the restriction map is one of projection, right? We project down these. So we have here a 3 tuple. We have 3 values, 1 for British Columbia, 1 for Alberta, 1 for Saskatchewan. And having those values, these are set maps. This is a function. And the job in life of this function is to take this 3 tuple, throw away the last value, and just give the first 2, BC and Alberta. This one correspondingly, but it throws away Alberta. This one correspondingly, it throws away British Columbia. And same thing down here. Same thing down here. Mm-hmm. And down here, we have no value, it throws away whatever it has, and this is the unit. It's the only possible value, Now, I mentioned this commutes, so this has to commute, and functions compose, so pure functions compose. So, going this way, trace this out in your head. If I have this 3 tuple and I throw away the value for Alberta, and then I throw away the value for Saskatchewan to get to the value for British Columbia, it has to be the same as if I throw away the value for Saskatchewan here, and then I throw away the value for Alberta. Does that make sense? It's kind of a commonsensical notion. It has to commute, right? So here we have a representation of values over this space that's different than the details here, but is capturing some relationships here. I do want to draw attention to the fact, and I don't want to miss out on the fact that I think you would agree that if we had a database that recorded products continuously in stock for different intervals, if this said something like AB, AB, H and F, I think you'd agree that wouldn't make sense because there's a logical constraint here that says that anything that's here, like H, will have to, of necessity, be here. It just, from the logical structure of the situation, if it's a product continuously in inventory from February 1st to March 1st, it must be the case that it's in inventory on February 1st itself, right? Similarly, if there were something here that if you had H here, it wouldn't make sense because it's positing something that's impossible, that it was continuously in stock here, but not here, etc. Similarly, if you were to reason about this one, if this included an H, that wouldn't make sense, and it wouldn't be consistent with this one here. Moreover, okay, I won't get into that. But I will say, yeah, I mean, so if this had H and this had H, but this did not have H, for example, that wouldn't make sense, right? If this had H, this had H, this did not have H, it wouldn't make sense because this has to be a strict superset of this, because anything that's continuously in stock January 1st to March 1st has to be continuously in stock from February 1st to March 1st, right? So if even if you had H here and H here, but not here, it wouldn't make sense. So what I'm telling you is this structure, there's a logical form of this structure for what it means to be a consistent picture of what's going down here, down in this space. If we consider this as kind of what's the behavior over this space, that's what sheaves capture. And Presheafs, even used in this way, capture behavior over these spaces. There's logical rules for it that we can capture by rigorously reasoning about these maps. And in fact, there's automated ways to check these things. Do they apply to a database? So what you're capturing is the hidden rules of structure that link up different data sets. You might naively think, well, it's just data, it's just data, it's just data. That's it. It's not just data. It's data that has to be consistent in certain ways for it to make sense. And what we're capturing here, in which sheaves more generally, Presheafs and where needed sheaves, is the kind of rules for the essential heart of the matter for what it means to have consistent data about a space. So same thing here. Like if the value for Saskatchewan here was different than it was up here, it wouldn't make sense, right? You might have data for the number of cases in Alberta and data for the number of cases for all three, and it has to agree. I'm not showing it here, but a variant of this that really gets into co-sheaves would moreover say that it wouldn't make sense if you said there were 30 cases for British Columbia, but 25 for British Columbia and Alberta together. That wouldn't make sense. It doesn't jive, right? How can it be 30 for British Columbia on its own, but only 25 for the two of them? That's what, again, something you can capture. Okay, so now let's look at another one. This one is a little bit more similar to the first, or to this one, I should say, with products continuously in stock. Let's suppose you were reasoning about sets of interventions that were in place across the jurisdictions. And I apologize for the small wording here. This says interventions across, meaning interventions throughout, like interventions uniformly in place across these provinces. Maybe these are public health measures. during the COVID-19 pandemic. So maybe for a given interval, there was a given intervention that was consistently in place between these provinces. And what this, I'm sorry, so this is our same space, and now this is the data about it. And now notice the relationships here. These are morphisms. They are contravariant. They're contravariant because they are going to reflect restricting down here. That contravariance comes from this being a presheaf. So it's a map from C up. So this is C up, flip arrows. It's a functor from that into this other category involving sets and involving function. So if you have a set of interventions across British Columbia, Alberta, and Saskatchewan, the set of interventions that are in place across all three entirely throughout that entire region. And now we want to consider those in place across British Columbia and Alberta. What's the relationship of this? Which set is larger? Which set could be larger? Is it the interventions in place across all three, throughout that entire region, that will be larger than those in place across just BC and Alberta? Or is it possible that if we consider those just in place across BC and Alberta, that that's larger than this? Which could be larger? Yeah, exactly. BC and Alberta, you might be fooled to think, well, smaller, so it's going to be a less large part. But the point is, again, as Daniel Rosiak emphasizes, this is more constraints. To qualify in this set, you have to be in place across BC, across Alberta, and across Saskatchewan. This subset, this set here, to qualify, you only have to be in place across British Columbia and Alberta. You don't have to be in place across Saskatchewan. So this could be larger. Do you get that sense? This could be larger than this set. This is more constrained. This is more restricted, or let's say constrained. This is more tight strictures on it. This has fewer strictures. So you can imagine a case where, for example, British Columbia and Saskatchewan have a public health measure in place that's not in place in Alberta. And so this would omit that one, but this one would have that one in place. Are we good with that? Okay. So similarly, if we map down here to just Saskatchewan or just BC, is it possible that BC has certain public health measures that are in place that are not also in Saskatchewan? Yeah, it's possible. So this could be a subset of that one. Each of these could map over, if we think of these as sets and functions, each of these could map over to one of those. Right? Each of these, this might have some that are not in this, but this is an injective function in that finds all of these must be in here because they're in the same place for these two. So it must be the case here. And moreover, if you map down, go like this, well, those functions must compose in the same way. In this case, it's not that interesting. This would be the set of interventions. Well, it's like the set of all possible interventions, set of all possible public health measures, because each of these must be in there.
Mathematics, intersection between three sets is the subset of intersection of two sets.
That's correct. Yeah, that's right. That's right. That's exactly right. Yeah. So here again, there's a logical structure, and if there were a list given to you that purported to be of the interventions in place in each in BC and Saskatchewan, another one for BC and Alberta, and another one for BC, Alberta, and Saskatchewan. And you found that there are some here that were not listed here. You'd say, wait a minute, this doesn't hang together, right? That it doesn't make sense to say they're in place for all, but why is it not in this list? And similarly, if there were something in the list here and something in the list here, if they were the same one, let's suppose intervention, call it intervention Z, is in this list, and it's in this list, indicating it was true in BC and Alberta. And Z was also true in place as a public health measure in BC and Saskatchewan. Then that implies that it must be in this list. Do you get that? Because, well, we know it's in place in Alberta and BC, but we know it's in place BC and Saskatchewan as well. So it's got to be in place for all three. So what I'm telling you is that this is picking up the logical structure of what must be the case here for it to make sense, for it to all add up, for it to be consistent. But once again, we have these set of kind of places or contexts, right? Here they are provinces. Here they are periods of time. Here they are intervals of time, let's say. And what we're doing is we're reasoning about data over those contexts and about the logical structure of that data. And we're recognizing that and this is absolutely key, that the relationships between these contexts, like that one is a subset of the other or what have you, give rise to structure, logical structure on the data over those contexts. It gives rise to, it implies logical structure, because commuting here means of necessity, for example, commuting here. The fact that there's an arrow here means that, in this case, there's a reverse arrow here. And this general picture is going to hold across presheaves and indeed for sheaves. But not only that, for co-sheaves. And with co-sheaves, we're actually not going to have the contravariance. We're going to have these turned around, and we're going to have cumulative properties. So we're going to have things like the interventions in place across at least one of these provinces, across at least one of these subregions. And there's going to be logical consistencies there. If for co-chiefs, if we have an intervention in place for at least one of British Columbia and Alberta, then of necessity, it's got to be in place for at least one of these, right? And there's this logical consistency mapping that's going to be implied by that. Similarly, if you have some number of cases across all of these, it's going to imply something about the number of cases cumulatively at higher levels, right? And again, per my comment, it doesn't make sense to say British Columbia had 25 cases in the past week, but British Columbia and Alberta together had 30, but British Columbia and Alberta had 25. That doesn't make sense. And so I'm telling you that those logical structures get captured by these relationships. And the relationships are implied by the context here, but the nature of those relationships will reflect the nature of these data, the data here. And if I could whet your appetite a little bit more, I'll just say, this is very much giving a lot of the picture of what we'll be dealing with sheaves. But one of the most exciting things in our context for our lab is that you can have sheaves that are not just valued in set, although we'll start there. But value in, for example, C sets. And where, if we're dealing with like intervals of time, we might have like a graph here, right? A graph that applies during this period of time. And as we go up for larger intervals, we might do something that like take its push up. And so essentially we combine what was in place for a subinterval for each of these subintervals to form something that's in place for this interval, for this entire interval. Reflecting with a push out, I recognize that's for Jeff, that's newer language, but that there's some overlap here. So we identify the period between the period of overlap here. I guess there's no overlap in this case between these two. February 1st to March 1st to March 1st to April 1st. But we take the push out. No, there is. March 1st is overlap. So we take the push out there. In any case, the point is we can have structured data beyond sets, beyond this sort of thing, beyond this sort of thing. We can have structured data and systematically take that data within these contexts and combine it within the context of the mappings implied by this base space. So this is going to be what occupies us for after we cover the remaining two chapters, namely the remaining two chapters before us of sort of more foundational material. So universal constructions we're going to talk about next. That's going to introduce the notion of a limit, a co-limit, a push out, a pullback, which are going to be really important when we have values for things that are not set based. And we're going to talk about topologies, which basically topological spaces, which basically allow us to reason about these structures, these systematic characterization of these contexts, including the relationship of one context to the other, like one is included in another. And we will see how these restriction maps will look different for different spaces of data and indeed different C sets we might have attached to them. But they honor some basic rules, like with for time period based data, we'll deal with pushouts and pullbacks for variously for sheaves or co-sheaves. Okay. So I think that's all for now.
It reminds me of the paper
Yes.
towards a unified serial
Yes.
data.
Yes.
I just recheck the cumulative and the persistent.
Yes. There you go. There you go. Yes. Yes. It comes out of this underlying mathematics.
Yeah.
But that paper, this unified treatment of temporal sheaves, also goes through the really exciting idea of taking, so it's not just a sheaf, temporal sheaf over set, it's a temporal sheaf over C sets. And that allows us to do all these operations because we can encode data that's very rich, not just as sets, set-based data, like the number of cases in the province. We can include graph-based data, or we can include data that's structured in a pre-order or what have you, and encode that kind of. Yeah. Okay.